today's video, we'll be going through Limits 101 with graphing, tables, numerically. We're going to find limits using piecewise functions. We're going to go and look at limits from the left, the right, and all of that. So to start, we're going to go off and look at limits graphically. Well, here we have a graph and we have some questions off to the side. It says to use the graph to solve the problems below. So we have the graph of f of x, which is right here. And now we're going to answer these questions. Let's go ahead and answer it in orange. Well, the first question asks us to find the limit of f of x as x approaches 1, and this negative sign just means from the left. So let's go ahead and do that. So let's locate 1 on our x, so that's 1 right here. And we want to see from the left side as we're approaching 1, what value on our y-axis are we approaching? And we can see that we're pretty simply just approaching this 1. So it's going to be 1. And it doesn't matter if this is a closed or open. There should be an open because we're just looking at limits. We're looking at how it approaches. We're not looking at the value at that point. Now, question number 2 asks us to find the limit of f of x, this graph, as x approaches 1 from the right. So from the right, we're approaching 1. So we have a y value of 1, and we're putting from the right. And we have a y value of -4. So that's going to be our answer for number 2. So the limit of f of x is x approaches 1. So whenever we don't have a sign like we do in this problem, that just means we're going to look at the limit from both sides. And for a limit to really exist, the value from the left and the right have to be equal. And if they're not equal, this means that the limit is D&E or does not exist. Well, we can see that from the left we have a value of 1, and from the right we have a value of -4, and 1 definitely does not equal -4, so that means we have a does not exist limit. Now, we have a question that says f of 1 equals blank. Well, whenever we have an open hole, it's not really equal there, so that means that either of these values are not our answer. But we do see that at 1, we have a value of right here, which is a filled in circle, a dot, and that's going to be our y value, or our f of 1 value, and that's going to be 3. So that is how we would do this first graphing problem. Let's go ahead and go to the next problem. This next problem, we have two graphs. This graph being f of x, and this graph being g of x. Now let's go ahead and look at the problems. It says, using the graphs above, evaluate the questions below. Should be below. Anyways, first question, limit of f of x as x approaches 2 equals. So remember, f of x is this graph right here on the left. And we're going to see the limit as x is approaching 2. Well, we can see at 2, from both sides, it's approaching 0. So we can assume that we have a value of 0. It's approximately 0. So our answer is going to be 0. Now, the second question is asking the limit of f of x as x is approaching 3. So again, we're looking at the graph of f of x on the left, and we want to see the value as x is approaching 3. Well, we can see that from the left, we are approaching infinity. It's just continuously going up. It's not stopping at a certain y value. And then from the right, we're stopping at -1. And since infinity does not equal -1, we have a limit here that does not exist. And if you want to write it out, you're going to say that the limit of as x approaches 3 from the left of f of x, because that's the graph we're looking at, does not equal the value of the limit of f of x as x is approaching 3 from the right. And that's how you would prove with a written limit statement that they are not equal. So we can go ahead and take that out. Now let's go ahead and go to the second set of these problems, which says that limit of g of x as x approaches 5 from the left. This minus is just the left. And again, the g of x graph is on the right side. So now if we're looking at it from the left, we see that we're approaching. We have a small open circle there, and then we're approaching 5 from the left. And it's just going to I'd assume that's approximately 1/2. And that's going to be our answer for this problem. Now it says the limit of g of x as x is approaching 3. Well, we can see that from 3 from the left and the right, it's the same value and it's continuous. So let's go ahead and just assume that's approximately 1. So that's going to be our answer for the limit of g of x. And now, finally, for the graph of g of x, it's asking for f of 4. So we're just going to look at our 4 and see if there's any value that is filled in or a proper dot. Well, we can see that we only have an open circle, but we don't have any dot. So that means that there is no answer for f of 4. Now, the crucial thing you have to remember is limits can be DNE. But here, where you're solving for the y value, the only answer you can have if you can't find a dot is going to be undefined. If you put undefined on a limit, because it's not a real limit, it doesn't exist. If you put undefined, the question will be marked wrong. And if you put DNE on a question where it's f of x, or f of 4, or f of 5, or whatever it may be, you'll get that wrong. So always remember limits, DNE, functions, undefined, whenever you're solving for the y value. Let's go ahead and go to the last two problems of this set. So now, we have the limit of f of g of x as x is approaching 2. So whenever you have something like this, you can think about it like you're taking the limit of the inside, and then you're taking the limit of the value you get after that. Well, we have an x value of approaching 2. Let's go ahead and look at g of x first. We're going to evaluate the limit of g of x as x is approaching 2 and see what that value is. So we can see from both the left and the right, we have a value of 2. So we have a value of 2. So now we have the limit. So now we're going to rewrite this. We know that this inside portion, if you take the limit of it, it would equal 2 because we just substituted the 2 in for our limit, for our x. We looked at the graph, saw what the limit was when we had an x value of 2 as x approaches 2. And now we're going to substitute that value, which was 2, into the limit of f. So we have the limit of f of 2 as x approaches 2. Because it's essentially just f of x, and we have 2 now. So now we're going to look at our f of x graph. And we can see that as we're approaching 2 from the left and the right, we just have a value of 0. So our final answer for this problem would be 0. Next, we have the question, limit of g of f of x as x is approaching 1. Again, we're going to split it up. So let's look at the inside portion of this first. So we're going to substitute in the 1 here for our x. So we're going to have the limit as x approaches 1 of f of 1. And we're going to look at our graph of f of x. And we can see that as we are approaching 1, which is right here, as we're approaching 1 from the left, we're pretty much getting -2, and from the right, we are getting also -2. So we're going to say that we have a -2 value. And we're going to substitute that into our limit of g of x. So now we have limit of g of -2 as x is approaching 2. So now looking at our graph at g of x as x is approaching -2 from the right and the left, we approximately have a value of 5. That's going to be our final answer for these problems. Alright, now we have limits where you're going to evaluate just with the statement. And you might have to do some factoring, you might have to do some multiplying by the conjugate, and with these fractions it's very interesting as well. Let's go ahead and start. First problem says that the limit as x is approaching 3 of x squared plus 15x over 2x. And the first step you always want to do is do direct substitution where you directly substitute the value that x is approaching in for x. Well, now we're going to do 2 times 3, which is just 6. And if it's 0, you have some further work to do if it's algebraic. And if it's not 0, you're in luck and you have a pretty simple question. Let's go ahead and complete this question. So now we're going to complete direct substitution. As soon as we have a value that is not 0 in our denominator, after direct substitution, we're going to continue direct substitution in our numerator. So we have a 6 in our denominator. Now we have 3 squared plus 15 times 3. So 3 squared is just 9. So we have 9 plus 15 times 3 is 45. 45 plus 9 is just 54. So we have a fraction of 54 over 6. And if you guys remember your multiplication tables, 54 over 6 is just simply 9. And that's our answer for this first problem. Now let's go ahead and do our second problem down here, which says the limit as x approaches -4 of x plus 4x minus 16 over x plus 4. Well, again, we're going to do direct substitution in our denominator first and make sure it doesn't equal 0. So we have -4 plus 4, and that obviously equals 0. Now that we know it equals 0, what we have to do is we have to try to factor the numerator. So let's go ahead and do that. So To factor this numerator, this factors out to x plus 4 and x minus 4. So now that we have x plus 4 and x minus 4, we're going to bring our original denominator back in. And we can see that we have a common term in both our numerator and our denominator, and that is x plus 4. Well, this x plus 4, we can eliminate it from both, and that'll just go to a value of 1, and we're going to be left with 1 times x minus 4. You may be wondering what happens to the eliminated value. Well, that eliminated value just signifies that we have a whole, and to get the value of the whole, this is unnecessary to the problem, but to get the value of the whole, you're just going to set that eliminated term to equal to 0. So we have x plus 4 equal to 0. That just means x equals negative 4. We have a whole at negative 4. You can substitute back in and get your y value into the simplified equation. Now, what we're going to do is we have a whole at negative 4. That's well and good. But now we need to find out what the limit approach is as x is approaching negative 4. And again, we're left with this simplified equation right here. Let's put it in a different color. We're left with 1 times x minus 4. And now we're going to do direct substitution again. So we have 1 times negative 4 minus 4, which is just 1 times negative 8. That just leaves us with negative 8, and that's our answer. So this limit, we can move all our work off to the side, and we can say we have a pole of some sort at x equals negative 4, and the limit is approaching a value of negative 8. Let's go back up and do this problem right here. Well, it says that the limit as x approaches 0 of 5 over 5 plus x minus 1/5 equals x. And to find your least common denominator in situations like this, just get this number, this 5, and multiply it by this 5 plus x. So we're going to have 5 times 5 plus x, and we don't want to distribute just yet. We're going to multiply both these fractions by this number up here, and this is not going to be a 5, this is actually going to be a 1. And if we multiply our negative 1 by the 5 times 5x, we can see that the denominator of 5 would just also eliminate. So we would be left with minus 1 times 5 plus x. And we originally have that 5 coming from this first part right here. So we're going to have 5 minus 1 times 5 plus x. Distribute this negative 1. So 5 plus negative 5 minus x. These eliminate and go to 0. And we're left with the negative x over 5x times 5 plus x, because this x was originally here, and we just multiplied it by the 5. And now we can see that x and negative x, let's go to negative 1. So we are now left finally with negative 1 over 5 times 5 plus x. So we have negative 1 over 5 plus 0 is 5, so we're left with 5 times 5. We are left with negative 1 over 25. And that's going to be the final answer for that one. Now we have these two remaining problems. This one is a bit different because we can see that we have a radical present in our numerator. Now here we have the problem, the limit as x approaches 3 of the square root of x plus 1 minus 2 over x minus 3. The first thing we want to do is multiply by our conjugate. The conjugate is just negating this value right here. So we're going to be multiplying by the square root of x plus 1 plus 2 over, and we're going to do the same thing on the bottom, multiplying by square root of x plus 1 plus 2. Multiplying by the square root gets rid of the square root sign, so we're left with x plus 1 minus negative 2 times 2, which is minus 4 over, we never want to multiply our denominator because it's often not necessary, square root of x plus 1 plus 2. Now we can see that this simplifies down to negative 3, so we have x minus 3, so we have x minus 3 over x minus 3 times square root of x plus 1 plus 2. This eliminates, so now we're just left with this term right here. We're left with 1 over square root of x plus 1 plus 2. And now we're going to just do direct substitution. We're substituting in 3. So we have final answer of 1 over square root of 4 plus 2. Square root of 4 is just 2. 2 plus 2 is 4. So we have 1 over 4. That's our final answer for this problem. Let's go ahead and look at relative growth rate. So we have the problem, the limit as x approaches infinity as x cubed plus 5x minus 6 over x squared minus 3x plus 7. And we have this note right here, which you might want to write down in your notes. Well, what it's saying is if there's a larger exponent in the numerator than the denominator, the function is approaching infinity. But if the denominator has a larger exponent than the numerator, it's approaching 0. For example, in number 1, we have a degree or an exponent of 3 in the top and 2 in the bottom, which means our numerator has a greater exponent and it's approaching infinity. Because think about it. If this value is getting bigger, this is also getting bigger, but it's not growing at the same rate or at a higher rate. So it's going to keep growing and growing until it won't stop. It's not limited. It's limited to infinity. So that's infinity. And then the second problem is just x to the power of 4 over x to the power of 6. We can see that 6 is definitely greater than 4. So we're going to apply the second rule and it approaches 0. Finally, we have the limit as x approaches infinity of 7 to the power of 2x over 5x. Well, 5 times any number is greater than 2 times any number. And this 5 and this 7, even though they're being raised to the power, what matters is the power itself, because 5 times 3 is 15, but 5 times 2 is 10. 5 to the power of 15 is greater than 7 to the power of 10. So that just means we are approaching 0, because the denominator is getting larger and larger, and that's making the fraction smaller and smaller. Let's go ahead and look at our limit definitions now. You must remember these or have them in your notes. These are very crucial in limits. First one is the limit as x approaches 0 of sine x over x is equal to a value of 1. And the other definition is 1 minus cosine x over x, and this is when the limit is as x is approaching 0. Or this could be written as cosine of x minus 1 over x. Again, the limit as x is approaching 0. These both are equal to 0. You don't have to really prove these with math or justify them. They're just definitions. Now we're going to table-based limits. Well, we have one table here, and it's representing the equation, which is limit as x is approaching 2 of x minus 2 over x squared minus 4. And it says to solve for the approaching x and f of x values. So we can see that we have a blank x value and a blank f of x value. We can see it's getting larger and larger and larger, and I think it's getting closer to 2 from our left. And from the right, we can see it's decreasing. It's getting closer and closer to 2. So I'm going to make an educated guess and say 2. Then down here at f of x, we have it's getting closer and closer to, I'm not sure, but here it's also getting closer and closer to a value that I'm not really sure about. So what we can do in scenarios like this is we can try direct substitution, and if direct substitution doesn't work, we're going to do the factoring like we did before. Well, if we do 2 squared minus 4, that's just 0. So that's not going to work. So what we need to do is factoring like we did before. But we can obviously see that we can't really do anything in our numerator, so we're going to focus on our denominator. Our denominator can factor out to x plus 2 and x minus 2 over, and our numerator is still x minus 2. Again, we can eliminate these, which just make a whole, and we're left with x plus 2. So now that we're left with x plus 2, we can do direct substitution. 2 plus 2 equals 4. So we can assume, and remember, we have that 1 in our numerator, so we have 1/4. And 1/4 is equivalent to 0.25, and that's going to be our approximate f of x value. And we did that after factoring our numerator, then doing direct substitution. Now we need to solve the limit from the right side of 1 over x cubed plus 7. And we have some notes off here to the side which say the smaller the denominator, the larger the value of the limit, and the larger the denominator, the smaller the value of the limit. Well, what we can do here now is we're looking at it from the right. So we're looking at it this way, and all these values are greater than 6. And everything from the left is lower than 6. So it's going to be negative, and that's why this is positive. So what's a value that's really close to 6 but a little greater? Let's just say 6.1. So we're going to substitute 6.1 because that's greater than 6, but it's not 6. We don't really care about what's happening at 6. We care about how it's approaching 6. And in this scenario, we're not caring about both sides. We're just looking at the right side. So the right side is the greater value. So that's why we have 6.1. I'm going to substitute this with direct substitution into our equation. So we have 1 over 6.1 cubed plus 7. 6.1 cubed is approximately 227. And we're going to add 17. So we have 1 over 244. And that's going to be what it's approaching from the right side. So we're approaching approximately a value of 1 over 244. Let's go ahead and look at our piecewise functions. Well, our piecewise functions, we have f of x equals 3x plus 5 when x is less than 4, x squared plus 2 when 4 is less than or equal to x, which is less than 5, 5x minus 4 when x is greater than 5, and 8 when x is equal to 5. So for items like this, what we really want to do is we want to try to prove where a function is continuous and where it's discontinuous. And we're going to talk about the different discontinuities at the end of the video. Well, right now, let's go ahead and figure out the limit as x approaches 4 from the left. And when it's to the left, it's the lower values, obviously. So we're going to look at this right here. It's going to substitute in 4 to that equation. So we're going to have 4 times 3 plus 5. So we're going to be left with a value of 17. So that means that when we have a value less than 4, we're going to have approximately approaching 17. And now what we need to see is if the value from the right of 4, or values that are greater than 4, if those also approach a value of 17. If they do, that means we know that the function is continuous. Let's go ahead and do that. So we can see that this equation is when x is greater than 4. So we can go ahead and substitute in, and we always want to keep our function statement right here. So we have limit of f of x as x approaches 4 from the right, and that's going to be this equation right here. So let's go ahead and substitute in. We have 4 squared plus 2. So 4 squared is 16. 16 plus 2 is 18. Well, 18 is not equal to 17, meaning we have a discontinuity. We're discontinuous at 4. We have some kind of discontinuity. Now, we have to look at from 5. So we can move all of this off to the side. I'll make it a little smaller. So let's go ahead and look at 5. So we have the limit as x approaches 5 from the left. This is left because its x values are less than 5 of f of x. And we're going to substitute that in. So we have 5 squared plus 2, which is equal to 27. So we have equal to 27. We're going to do the same thing, but we're going to look at it from the right. So we have the limit of f of x as x approaches 5 from the right. So we're going to substitute that into this equation right here. So we have 5 times 5, which is 25. 25 minus 4 is 21. 21 is not equal to 27. So we still have a discontinuity of some sort. That means we basically have a discontinuous graph right here. When x equals 5, we have a y value of 8. So we have this only point. So it's never continuous at any point in the actual graph. It's all discontinuous, except at the point 5, 8. There's no continuity anywhere else. Now, finally, we're going to talk about the types of discontinuities. First being a discontinuous point discontinuity. Here we're going to have a hole, as you can see here, as just an open circle. When you see one of these, it's removable. It's something you can fill in and it'll become continuous. Remember from our last video, continuous just means that you don't have to lift your pencil when drawing the graph. So now that we're here, what we can do is we can see that, we have a hole here, and that means from here to here, it's discontinuous. Now here we have a jump non-removable discontinuity. Something that's removable is something you can get rid of, and it would become continuous. Or something that's non-removable is something even if you try to remove it, it'll still not be continuous. So here you can see it's literally just jumping from, let's say, a y value of -4 to +4. So that y value jump is why it's called a jump discontinuity. And this is often found in piecewise functions. Now, lastly, we have an infinite discontinuity where we would have something like a vertical asymptote. And this is non-removable. There's no way of filling it in or fixing it and making this a continuous function. So it is a non-removable discontinuity known as infinite, where you can see values are just going infinitely, and there is an infinite discontinuity between the two line segments. So now, I hope this video helped. If you believe it did, please consider like and subscribe. I wish you guys the best of luck with limits. If you guys have any more review questions, please let me know. This video took over an hour to record, and now I still have to edit it. I wish you guys the best of luck again, and thank you so much for watching. Bye-bye.